All right, good morning, everyone. My name is Brian Holman. I'm going to be teaching the module on non-destructive evaluation. So this is going to be the first time we're actually doing this module. So I'm going to try to keep it more open-ended. And if you have specific questions related to research or things that you can ask questions, we're going to keep it open. The lectures are going to be geared towards more macro structures, so bridges, power plants, large assembled structural components. This way the schedule is going to work is today I'm going to be doing just a general overview of non-destructive testing, showing you some photos from past research and as well as site photos and a discussion on general visual testing, followed by ultrasonic testing, radiographic, eddy current, electromagnetic techniques, magnetic particle penetrant type inspections where you use fluorescent or other dyes. And then the last lecture right now scheduled to be for specialty materials, so something like a carbon fiber reinforced polymer or glass, or it can be if you have something specific you want us to talk about ND-wise, I can play around with the last lecture, as you guys need. So we're going to keep it pretty open, and the first thing is for people who haven't, been in industry and worked on engineering sites before, what is non-destructive evaluation? So in the US, the certifying agency is called the American Society of Non-Destructive Testing, ASNT. They define non-destructive testing as a process that involves inspection, testing, or evaluation of materials, components, or assemblies, and for materials discontinuities, properties, and machining problems without further impairing or destroying the part's serviceability. So it's kind of a long-winded definition. In the simplest form, NDE is the interaction of a component with some form of energy. So depending on what part you're trying to inspect, it will dictate where on this energy spectrum and which applicable techniques you can use. So if you're trying to inspect a metallic component, the thickness of it will dictate what depth of penetration as well as whether you have enough energy to actually interrogate where you want to see. So this example here is a section of rail, but it's not rail that a train car or the T passes over. This was actually a section of rail that a crane would have a gantry on, and actually the crane would move, and it was for a dredging operation in a river. And if you look at it, you see what's called a forging burst, and this was from the melt process when it was coming out of the steel mill. It's also known as just a general inclusion. But this is a good example of something that if you just looked at the top of this crane rail and did a visual, you would miss it. And when you have something that weighs many, many tons moving over the top of it, there was a concern that it would actually have fractured the rail and the crane would have fell into the river. So if you walk around Kendall Square, you see construction sites all over. You see cranes in the air, you see heavy construction being performed. So these are some things that if you haven't thought about beforehand, this is kind of what the module is going to deal with. So you could look at this one. So based on the spectrum, the size of the part, the thickness, that will dictate whether you can use millimeter wave technology, thermography, infrared, X-rays, or some other form of energy to interrogate the sample. So similar to how Professor Eager discusses welding as being ubiquitous and welding is a part of general life, the same thing applies to non-destructive evaluation. NDE is performed daily basis for many industries. Transportation, rail. If you commute into Cambridge, there's something called a Sperry car that goes and does ultrasonic testing on the rail at night to make sure that they don't have similar type of fault, flaws, and defects that you see with the cargo rail. Maritime shipping, they use it for inspection of the container crates and things like that for whether there's corrosion issues. They are also, one of the things they're doing now is using handheld X-ray, portable X-ray systems for detecting if people are trying to smuggle things. So whether somebody puts something in a tire in their vehicle and tries to get things across the border, now they're using non-destructive evaluation to see if they can detect things. Same thing when you go through the airport. Now you go through the scanner. That deals with millimeter wave technology. So construction industry, aerospace, it's relevant, throughout all the engineering disciplines. The last one, the energy. So Professor Belmar is going to be doing his lecture tomorrow. His startup actually deals with a technology for in situ non-destructive inspection for oil gas lines. So these are of high value to oil and gas industry, because in those industries what happens now is you have to actually divert the pipeline or however the product is flowing, and then you cut out a sample and do destructive sectioning to get material properties. So the material properties could be fracture toughness. This would be a Sharpie bar where you look and see where a material may have a ductile to brittle transition. And if you're in the Arctic, you have to deal with cold temperatures. These are things that are relevant to the environment that the oil and gas is coming from. So you can see that as well. So as opposed to actually doing destructive sectioning and taking a metallurgical sample, this module is going to deal with trying to get material properties without having to actually section the sample. What you're going to see in this is a mount, and it's a weld at this L right here. And the dots on the top are micro hardness indentations, but you can actually look at, and just visually, you can see where there's a gap between the weld and the base metals. The other thing is, for those of you who are in the material science department, you also have an example of how not to mount. You're not supposed to have this cloudy appearance when you mount samples. So I'm not sure how many of you actually do metallurgical prep, but there's a couple things going on with those samples. What you're seeing in this image here is actually what's referred to as a test cell facility. So when you have airplanes that are in service, when they pull the engines off to do routine maintenance on the engines, when they reassemble the discs and the blades in the engine, they have to actually put it up to speed before it's allowed. FAA, Federal Aviation Administration, allows that engine to go back in service. So what you're seeing in this image is a test cell where they actually have an airplane engine and they speed it up. And if you're interested, I can bring in videos where they actually throw in frozen chickens and they do ingestion tests for the engine, similar to what happened with the double bird strike on the Hudson when the captain landed the plane in the Hudson River. They actually, before they certify a new engine, they do these types of tests in test cell facility. So some factors involved in the choice of your method is what I discussed before. The geometry as well as what type of material. So whether it's a carbon steel, whether it is an alloyed steel, a non-metallic, metallic, carbon fibers, these things will all affect what techniques are applicable if you're looking for surface flaws or subsurface flaws. So The other thing that's important is the operational history of what you're inspecting. So if you're trying to inspect the oil and gas pipeline, whether it's in Texas or whether it's in the Bakken Shale in Canada or whether you're in Dubai, the environment where that component operates is relevant. Things like humidity and how aggressive the salt or area does affect whether you're going to be able to use certain techniques or not. Whether there's a welding process or some other type of process to join the parts together is also important. So in some cases, you have dissimilar metals. So if you're trying to weld a carbon steel to a stainless steel, the fact that it's not the same material is relevant to whether you can detect if there is going to be a lack of penetration or some other type of flaw. The inspection rate, how quickly you need to get your data versus the cost. So you can do many techniques, but ultimately if they can do one cheaper than the other, the cost is normally the driving factor for what ends up getting done in the industry. So the first example I'm going to give, because a lot of my research was in dealing with aerospace, so airplane engines. So the first example is going to be on the evolution of turbine blades, and this relates towards the material science and the microstructure and grain structure of the blade. So in the 50s through the 70s, they had initially conventional casts. And then when you look at that grain structure, when you're operating a jet engine, you're actually operating it above its melting temperature when the gas goes past the combustion stage into the turbine inlet stage, you are above the melting temperature of the components that make up that engine. So in order to be able to fly and not have components melting and failing all over the place, what they went to initially was a directionally solidified type of structure. So you wanted to limit the dissimilarity of the grains, because the grains is where your weak links are going to be for either oxidation or high temperature corrosion, things like that. And then once one of those grains, you either get pitting or some other type of failure mode there, it will fail quickly just because you're operating at such a high temperature. So what they ended up going to was the single crystal design for the turbine blades. So I'll bring it in for the next lecture, I have some blades. When you actually look at the blades, that is a single crystal component, the way it's fabricated. And because of that, you're able to operate the planes. Now, over time, as they wanted to increase the efficiency of the engines and inlet temperatures, what they did was they started adding other design features. So what you're seeing here is actually laser drilled holes which act as cooling channels, because the blades have internal cooling passages. So while the hot gas is passing on the outside of the blades in the engine, you have cooling channels within the blades keeping them from overheating. But there's so many failure modes that can happen, all right, especially with turbine blades, because turbine blades usually have what's called a thermal barrier coating, which is a ceramic slurry type coating over the metal. And in the TBC, you can have a lot of failure modes. So you can have the wear, oxidation, or corrosion at the tip. This area would be called the leading edge, and this would be called the trail. This is the leading edge here. This is your trailing edge. That deals with the path of the hot air past the component. You can have issues at this dovetail connection at the base here. So there's a lot of failure modes that can present themselves just because it's in such a harsh environment for the blades. So these are things that people, when they get on an airplane, generally don't consider. But if you've ever been on an airplane and lost one of the engines on the plane, it's not a fun experience, because it makes quite a, if the blade actually, it's an uncontained event and the blade gets evacuated, you'll know it if you're on a plane and this happens. So this is an example here. This is what happens when it goes wrong, okay? So this is, I believe this was a stator vane on an engine. And what you're seeing here is, depending on how thick the coating is and how often they repair and replace that barrier coating, you can have issues related to corrosion, sulfidation. The other thing that people don't generally consider is where they're getting the fuel. So sometimes there can be more crude components. So that sulfidation relates to where they're getting the fuel and how the fuel is being refined. And if the fuel isn't refined properly, there'll be trace elements in the fuel that will be aggressive to your engine, the metallic components in the engine. So what you're seeing here is this was on a flying airplane, and that's what happens. So how many people here have been down to New York before? Most people, right? So at the end of the class, I'm going to show you a video from top of the World Trade Center Observatory. But one of the things I want you to think about is just, this is a photo looking down at New York from top of the Freedom Tower. How many opportunities for different types of ND inspection do you see in this image? And there's thousands. So you think of all of the skyscrapers in New York were built with, welding and steel technology. You have to do inspections on those structural steel components. So you can't cut the steel out and bring it to a lab and do it. You have to do it on site. So that dictates what techniques you can use. So whether it's magnetic particle, whether it's fluorescent penetrant type inspection, that dictates what you can inspect for the steel. But you also have concrete. All right, if you wanted to inspect the concrete, you could use techniques such as ground penetrating radar, or there's other ND techniques specific to concrete, because at the microstructural level, concrete is much more inhomogeneous than carbon steel or other types of metals. All right, the other thing that people generally don't consider is that you also have to inspect the glass. All right, you're over 100 stories in the air, and the only thing keeping you from falling is what's called the curtain wall of the building. And you can see the reflection of the glass here, but that glass is actually manufactured specifically for where it's going. And they have what's called IGUs. That's the panels that the glass is. So there was a news article a few years ago in China. They actually made a bridge, and it was a glass bridge, and people were walking on it, and they had to close the bridge down because someone went on the bridge wearing high heels and didn't realize that point loading from wearing a high heel actually fractured one of the layers of glass. Now, they build redundancy into these structures, so they have double IGU and triple IGU designs. So just because a single glass panel fractures doesn't mean somebody's going to fall through, but it does mean that they did have to close that bridge down to repair it. And that then opens the question to build a scaffolding on a bridge in, where it's 1,000, 2,000 foot span. That is a whole nother set of engineering problems that then come up when you have to do maintenance work. So at the end of class, I'll show you the video, but just something to consider, that all these different types of inspection techniques, they're material specific. So you would not use the same technique to see if there was a flaw in the glass that you would use for the metal. As I said before, ASNT is the organization in the US. So this would be if you ended up graduating and going working for an engineering firm that does architectural engineering type work, you would have people at the firm that go and do these types of inspections. They would need to get qualified for ASNT certification based on the technique they're going to use. So you can't just say, I do NDE. You'd have to say, I'm certified to do ultrasonics. I'm certified to do fluorescent penetrant. And there's regulatory requirements on how many hours that you need to be working in the field before you can get certified. So these are things to consider when you enter the real world and you actually have to go working on, structures, or whether you're a designer and you're actually building something, to think about before a building can have people occupy it. It needs to get signed off, and you need to show that it's not going to collapse. In other countries, they have their own organization. So in UK, it's called the British Institute of NDT. In Germany, they have a lab called BAM, which basically just translates into the German Non-Destructive Testing Center. But these relate to different countries have different regulations. In the United States, AWS is American Welding Society. So for any high-rise building or large structure like university campus building, if there's structural steel, it's AWS D1.1 is the structural welding code. So that's Professor Eager already has a separate module just on codes and standards where he discusses these factors. So when you're dealing with NDT, a couple things you need to consider. Are you looking for surface crack, or are you looking for something that is going to be like on that crane rail that is embedded into the structure subsurface? And this chart here just says, not every method is applicable to every type of flaw. So if you're trying to find something that, if you were at a site and you're dealing with a concrete bunker that is 1 meter or 2 meters thick, you are not going to use a technique that can only detect, millimeters. You'd have to do something, you have to take into account depth of penetration. So when you're dealing with something of that sort and you have to inspect into a thick structure, the two main techniques are going to either be X-rays or ultrasonics. And there's trade-offs with each. If you have to use X-rays at a high accelerating voltage, you'll have to close the site down. So you can no longer have people be doing work in the vicinity of where the inspection happens. That's why the AWS code has actually been modified over the last 5-10 years to also allow for ultrasonic inspections so that you don't have to clear the site by doing ultrasonic inspections. But ultrasonic inspection is material specific. So you can have what's referred to as ultrasonically noisy material. So if you're working with titanium alloys, aluminum alloys, or things like that aren't homogeneous, the trace elements and what's used to actually fabricate the alloy will affect how the ultrasonic waves scatter when you're trying to interrogate the sample. For surface discontinuities, eddy current technique for aerospace is typically used, and the eddy current technique deals with electromagnetic interrogation of the sample. So this is just a still. I'm going to show you the actual video, but what you're seeing on the screen here is this is the point probe in the inspector's hands. It has this was a 2-channel probe, so that how many channels is how many electrical signals are being sent out at any single time. This would be considered an old equipment. Now they have equipment that can do 32, 64, 128 channels simultaneously. And what you're seeing at the output here is what's referred to as the Lissajous signal. And it's at a 45-degree angle, and it's indicative that as he was scanning over, this is called a duct segment, as he was moving over this area, he was not flush with the sample. So the duct segment sample actually had a taper to it, and you'll see as he tries to scan over it, as he's scanning over it.
So is that telling you since it's almost at a 45 that the notch isn't aligned as to what your calibration
No, it's
is?
not too much that. I think it starts to this is a wear spot.
Yeah.
Lifts off a little bit. You're looking at a little bit of lift.
So you actually, based on the scan here, he can tell that it's not, the data he's getting isn't relevant because of the liftoff. The other thing that's important from this example is the other thing you see in this image that you need to consider is this would be what he's using to calibrate the equipment. So how are you going to make sure that from sample to sample, if this is an industry where you're doing this continuously and you want high throughput of your samples, you have your reference sample here, and then you can make sure that you can do the inspection to a known standard. Fabrication and how the component's made is relevant. So I showed you with the example for the turbine blade before, the cooling channel holes. So this is an example of laser ablation, how they actually put those cooling channels in to the sample. It sends a laser pulse, and the laser ablates that metal at a known depth to get those cooling channels. So this is actually, it's in inner atmosphere where that laser operates, and how the pulse goes on and off is all programmed in before they do it to make sure that they don't keep the pulse on too long. You'll ablate too deep into the sample, and that will be a weak spot for crack propagation during operation. So those are just a couple examples of real-world applications. So some things to consider, inspection variables that are relevant, and they are going to affect both the probability of detection as well as the confidence level in the technique, are what type of flaw are you looking for? And are there potential artifacts that will lead to false positive indications? That's relevant for ultrasonic inspections. They're called ghost echoes in the data. The object that you're testing, the equipment. So the equipment can actually be a source of electronic noise. And if you are looking at something where you're trying to determine microstructure, like 300 micrometer size flaws for something that is not macro scale, the equipment that you're using, the noise, electronic noise, can be enough to result in false positive indications. So ultimately, and the last one, human factors. So if it's a visual exam or it's something where it ends up being an inspector has to make the decision on it, there are human factors that tie into reliability. The person's eyesight, as we'll talk about in visual exam, there's quite a bit of variability in in detection simply based on individuals' eyesight. So probability of detection was a concept first introduced in the 1970s, and it relates towards fracture mechanics and Griffith theory, and it deals with trying to predict crack growth properties. So both the rate of crack growth as well as when initiation of a crack will begin. It was relates towards the confidence at which the technique has. So in the industry, if you're dealing on a regular basis with non-destructive testing, you'll see it listed as so POD, probability of detection at a confidence level. So generally it can be 95%, 90%, and down. And what the standard is for aerospace is a 95% probability of detection at a 90% confidence level. So this is where statistics comes into play with how many samples are you inspecting. The more samples that you inspect affects the confidence bounds. So the thing that is important to understand with probability of detection, that it's somewhat counterintuitive, it is not the smallest flaw that you can detect. That's not the critical parameter. What's the critical parameter is it's the largest flaw that you can miss. So it's the misdetection is more important than how small of a flaw you can see. So it's a trade-off between can you detect it or how reliably can you detect it. This concept is applicable more towards surface cracks. So trying to get an idea on crack propagation rates. It's not directly transferable when you're dealing with inclusions and subsurface flaws. So your signal to noise ratio, regardless of which NDE technique you're using, you're going to get a signal as your output, and then you're going to get noise based on the type of material you're inspecting. What you want to be able to say, the way you're able to say you can get to that 95, 90 PODCL level is how do you discriminate between the signal from the NDE equipment and the noise from the grain structure of the material you're testing. So at some point, at some threshold point, the smaller the flaw you look for, the noise is going to go up, and that is what they're showing here as a threshold level. At some flaw size, you can no longer reliably say whether you detect it or not because of the materials, how it's manufactured. And that's important to know because I deal with NDE a lot and I see a lot of new equipment coming out, and a lot of these, techniques will claim that they can inspect things that they really can't. It's not the fact that they can just inspect it, it's can you reliably detect this flaw size? So that's why it's not the smallest flaw that you should be looking at in their brochures or published data. It's at which flaw size can you meet the confidence level requirement. And if you, as I said before, if you can miss the flaw, it's as detrimental to loss of business interruption and issues on a job site if you have a false positive indication. So you can either miss the inspection and not see the flaw, or you can think that there's a flaw and it's a false positive indication, and then go and do remedial activities when you don't necessarily have to. So it works both ways. It works both ways, and one of the later slides shows it's basically a 2x2 quadrant. It's was there a flaw? Did you detect it in one corner? Was there no flaw? And was there no detection? And then you have false positive, and then you have missed detection. So they're both important because they both affect what this confidence level value is going to be. If you have a false positive, what happens is if you're trying to get certified by a government agency for, if it's an airplane engine, it's FAA. If you had a false positive, what then happens is they make you do a number of more inspections. So there's added costs due to false positive inspections. So for the number I'll throw out there is there's a military, it's called Military Handbook 1823, and that's in the US what deals with NDE for engines. In general, to have a statistically relevant test, you'd have to do a minimum of 30 inspections. If you had a single false positive, then the number jumps up to 60. And then if you have two false positives, it's like an exponential increase. So it's relevant because on airplane engines, we have entire sections of the engine that are made from ultrasonically noisy materials, and in particular, titanium alloys. So one of the reasons why titanium is microstructurally and ultrasonically noisy is because it's allotropic, and it goes from hexagonal close packed, which is known as the alpha phase at room temperature, to a body-centered cubic. So there's actually a transformation of the structure at a specific temperature. All right, this is your phase diagrams. This is your basic material science, intro to material science. What happens is, though, it leads to issues with the inspection techniques. And what you're seeing in this image here, this is what's called the alpha case. So it's the alpha phase, but it's basically a protective layer that builds up over the titanium to keep it from corroding. Then when you look at it when it's milled, it looks shiny and it looks like what people generally consider when they think of titanium. If you have to perform a surface preparation activity before you do the inspection, it's relevant. So if you did an inspection, you did it through the case layer, you're not going to get the same output as if you perform the inspection and you removed a layer of material. We're going to talk about radiography as its own separate lecture, but one of the things that's important to know is with respect to radiography, there's been advancements due to advancements in computing power and processing power. So years ago, 100 years ago, they would just do traditional film radiography. What you're seeing in this image here is this is the cooling passages in a blade, and this is after they performed a maintenance and repair process. They had what's called a post-weld tip crack on the leading edge. Now they have techniques, rather than using a traditional film where you put the sample down, it takes a single x-ray, and then you look at it like you're at the doctor's office, and you can see some, now it's digital. So they've gone to both digital radiography as well as what's known as computed tomography. So in this image here, what you can see is, so this would be a titanium implant in the tooth. And because it's a different density, it shows up as different grayscales in the radiograph, as well as if there are composite amalgams and things like that, versus just the root, the bone and the root in an individual's mouth. This video here, I'm going to show you. So this is what they're doing now in computed tomography. Rather than taking a single x-ray, it takes thousands of x-rays and it renders it, and then you can get basically 3D models, and you can import it into CAD, CAM programs. So if you deal with SolidWorks or something like that, you can import the scan data in, And you can actually, it's used for reverse engineering of components. They use it, and it's not just aerospace, they use it to reverse engineer components of many different, material structures and for applications. So what I want to show in what I want to show as an example for the computed tomography is, this is going to be an example of internal to the blade. You would never be able to detect what you're going to see here on a visual or a surface technique. The other thing to notice is, as I go through the projection of images here, you see those two bulges that happen on the inside there? They're called blisters in the blade. And the blisters are coming about because of attack from the inside. So rather than the hot gas path causing oxidation or corrosion, this is actually from the ID of that blade. And by doing the computed tomography, you can then render it, and you can not only see that there's more than one blister in the blade, you can see that they're in relative proximity, and then you can see one size of one versus the other to be able to pull it out of service. Because that type of feature that you can't see with your typical inspection techniques, that would be something that would have caused the blade to actually become dislodged from an engine in service. One other thing you may not be able to see very clearly on the images, as I went through the various x-rays, you see some, there's what's called, halo effects, or there's effects from the x-rays that you can see as it goes through different slices, 2D slices. So for ultrasonic techniques, it's based on sound waves. Whether you're in a doctor's office and you're a pregnant woman and the doctor's doing sonogram, or you're in an industrial site and they're doing, ultrasonic inspection of, engines or something else. It's all based on the interaction of the sound wave with the material under inspection. So it's not, the thing that's important with the acoustics is there's multiple ways that you can use sound waves for your benefit. You can use longitudinal waves as well as shear waves, and you'll get different results that are applicable to different types of flaws. So this will be a different lecture, but what you're seeing here is this is a piece of equipment at UMass Dartmouth, and if you were dealing with a large component, this whole bath would fill up, and the component would sit on the bottom here, and it does a 2D raster scan as it goes through the part. Since I wasn't dealing with components that needed to fill that whole tank up, we just put it in a smaller thing and filled that up. But this is the component being inspected in here, and it is underwater, and the probe is actually going in a XY direction as it rasters over that location. The latest and greatest in ultrasonics is phased arrays. So this is where I was discussing how you can actually pulse the probe elements. Rather than a single probe, you can do 16, 32, 64, and you can sequence how you pulse the ultrasonics. And that allows you to actually steer the UT beam at angles through thick components. So that allows you to do what's called, this is a sectorial scan. So it's actually like a slice scan. It's not It's not a longitudinal where it's pulse echo, where it's shooting straight down and it's just a pulse, it hits the back wall and comes back. This actually is going through and it's steering through the component at some specified angle based on your transducer. But what that allows you to do, being able to pulse the beam, is now you can size. You have much more capability to size the flaws. And this right here would be 1/64th of an inch. So we're getting down, pretty small flaw sizes that you can find. Visual inspection, talked about most of this already. Important with visual inspection, if you're just, the limit of the human eye to detect the flaw is, in general, the rule of thumb about 6 millimeters, depending on what you want to do. Now, you can see smaller flaws than that. It also depends on accessibility at the site, but there's high variability from inspector to inspector. So that's really one of the more limiting factors. The variability from inspector to inspector, can be an order of magnitude. So if it's a critical application, if it was for something going up to the space station, you either want to have redundancy in the inspection process, or you want to have more than one inspector confirm whether it's, so you don't get false positives, because access to components, if something's in space, you don't have access to it. If something's 100 stories in the air, and it's not easy, first of all, to get up to certain sites. And if you're dealing with curtain wall, then you have to build some type of scaffolding off a building, and these become limiting factors in industrial inspection. So this is visual inspections, not just with the eyes. This is what's known as borescope. So borescope inspection is when you would have to actually snake the borescope into a component that you can't visually look at. So this is a turbine blade, and you're seeing the spallation of that ceramic thermal barrier coating. So this is from a borescope, and so that's just so you know that visual exam just doesn't mean look at it with your eyes. There is equipment involved as well. So I'll get to these next week, but I want to show you just a video here, so we can cut it off the video for now. I can post the slides as well if you think it's helpful. One of the things for next week, I put what I consider to be interesting, relevant NDE articles onto Stellar. So if you pick one of them, they're like 5 or 10 pages, so it's not like a huge task. If you can read one article that interests you before next week. But just for an example, the one related to railroads. So rather than crane, this is for actual railroads. One of the articles I posted, and it has actually interesting fracture surfaces on different flaws and how they inspect it. So the last video I want to show you guys is from, if you haven't been in New York and haven't gotten to see the observatory, this is the video they show you when you get there. And I think it's cool enough that. So this is at the top of the, I call it Freedom Tower, but it's New World Trade Center. And this is kind of like their advertising that they're showing all of New York, how New York has all these industries. But what you're going to see is this is actually, this curtain lifts, and then the picture I showed you earlier is what is after this curtain lifts. notice one of the issues in New York City after Hurricane Sandy and all of the salt water that came into the MTA and Long Island Railroad and other sites, corrosion because of the chlorides became a very big issue. So they were doing inspections of these tunnels because the water level, when you figure the subway's underground, the water covered the entire subway. So now you have issues. It's a adverse environmental effect due to natural disaster, and how do you inspect it? So I thought it was pretty cool. And then you get a 360 view of all the buildings on top. So I actually had worked at it before they opened this building up. So to see it 15 years later after they're done with most of the work was pretty cool. So if you guys have questions, next week I'm going to gear it more towards mag particle and penetrant type inspections. But if you have specific questions, let me know and we'll kind of keep it open. So I want the module to be useful for you guys for if you're doing research or if you have co-ops or things like that. Thanks a lot.